Okay, so let's discuss um, another basic algorithm that uses recursion, which is MergeSort. Okay, so most of you have experience with MergeSort already. We're just gonna view it through a more theoretical lens and see how we could describe the algorithm itself. Okay, so um, so MergeSort. Let's define the problem. Given a Given an array of elements, we want to rearrange that array so that the elements are in ascending order. Okay, so for instance, um, we have a input. Let's say the input is algorithms. We want to rearrange algorithms the so that the array is in ascending order, i.e. we want to make it so that it is in alphabetical order, which algorithms currently is not. Okay, each of these letters has an ASCII value, and any programming language can compare letters according to their ASCII value. Can compare. Um, so what do we do? Well, in merge sort, we simply divide and conquer. Okay, merge sort is a very basic form of a divide and conquer algorithm. Basically, we have a n element array which needs to be sorted, and we say to ourselves, well, it's really difficult to sort n elements all at once. You know what will be easier? If we sort half the elements first, and then we sort the other half of the elements next, and then we merge the two sorted lists together. So that's what we do here. We divide the array into two, okay, and then we sort them. Okay, so Algor it's transformed into Aglor, and Ivms gets transformed into Himstit. Now these two subarrays are sorted, and so now we have two sorted arrays, and it becomes very, very simple to simply combine them into a sorted larger array. For instance, we merge them, and what do we do when we merge them? We simply say, okay, is A larger or H larger? Is A smaller or H smaller? And we, of course, say A is smaller. So A goes first element into the new sorted array. Next, we go, is G smaller or is H smaller? And we say G is actually smarter. So it goes the next element into the sorted array. Then we say, is L smaller or is it H smaller? Well, H is smaller. So that's the next element in the sorted array. And so on until we have a n element sorted array. Okay, so that's the merge sort that you know from Programming 101. Okay, that's a merge sort that you first learned recursion, first learned how to do with recursion. You probably learned this right after you learned a bubble sort. Okay, so the question is, how fast does this algorithm run? Okay, how fast does this algorithm run? Because we know we have merge sort, it can be described by a recurrence that we just write as t to the n, and we know these two elements take t to the n over 2 time and t to the n over 2 time. Okay, however, how long does the merge itself take? Okay, in the Tower of Hanoi problem, the part that wasn't a recursive call, it took constant time, right? It was one move. That was the constant time. In merge sort, the part that isn't the recursive call, well, it seems a little bit more complex than constant time. I mean, if these two halves were 1,000 elements long each, then presumably the merge would take significantly longer than if the two halves were each 1 element long. Okay, so we merge it by looking at each spot, as we described before. And so we notice that the merge function itself uses constant extra space or constant extra time. Right? Space and time are sort of linked. We'll discuss exactly how later in the course. But we know that doing this merge operation, we look at every element, we do n comparisons, right? For every element in this sorted list, we actually did a comparison between the first element left on each half of the sublist. Okay? Okay. So that's our merge sort algorithm. So we have this merge sort algorithm, the formal code. We have if the algorithm is larger, if the array is larger than one. That's important because, if the array is only one element, then it's already sorted. But the sort only matters if the array is larger than one. We simply find the middle spot of the array, the middle index, I should say, of the array, and then merge sort each half, and then merge the two halves together. Okay, so how long does it take? That's the question. How long does it take? And so we know, let's start out, let's say the number of elements is 16. So we have a merge sort, so we call two merge sorts of time 8, of 8 elements. And then those merge sorts each call two merge sorts of 4 elements. And then those merge sorts each call two merge sorts of 2 elements. And so each of those merge sorts call merge sorts of 1 element. And then again, when we get down to the bottom of this recursion, this is our base case. So remember in our function, if n is not greater than 1, we just simply return the value, and then the merge takes care of merging these 2 elements into a sorted subarray. So we know that merging 2 sublists, the merge for n elements takes 16 time, right? We know that from the previous function. The merge function, the only thing that does any actual work in this algorithm, takes 16 time. So we know also that if we go down a level, the merge sorts for n over 2 elements, the merge sorts for 8 elements, the merge inside those merge sorts each takes 8 time, right? And so on. Each of these merge sorts, because n is equal to 4, it takes 4 time. And then we go down, and then we get the complete tree. So we have a bunch of recursive calls here. We have a bunch of recursive calls, and each of those recursive calls has a merge function in it, which takes n time. Okay, so the question is, how much work is this? And how much work is this not only for 16, but how much work is this for n? That's the most important thing. Okay, so T of n is the time it takes the merge sort to sort n elements, n element array. And so, as we discussed, merge sort n calls merge sort n over 2, and then it calls merge sort n over 2 also, the lower half of the array, then the upper half of the array, and then this right here is the time it takes the merge function. Okay, so the question is, how do you solve this? How do you solve this function? And there are many, many different ways to solve recurrences. Many, 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 many different ways. Now, as a computer scientist, as a mathematician, if you were a mathematician, we would go through all the different types of ways to solve this recurrence. Okay? And all the different types of ways to get an exact solution to this recurrence. So with the Tower of Hanoi problem, we said that recurrence is exactly equal to 2 to the n minus 1. Okay? But the beauty of being a computer scientist instead of a mathematician is that you don't really need to be that exact. Again, depending on the system your algorithm is running in, there's a constant time increase or decrease. Like it really, depending if you're running your algorithm on the newest M2 Mac, of course it's going to take less time than if you're running your algorithm on a 20-year-old Pentium 4 computer, right? So computer scientists don't worry ourselves with those, constant time increases or decreases. Okay, because life isn't perfect. Those constants, the constants before the the constants before the polynomial function, the n to the whatever, the n to the number, or the n to the n, or whatever. These constants, they're dumb. They're dumb. These constants don't matter. All that matters is the big stuff, right? The stuff that grows with the size of the input. Okay? So that's why we, instead of finding the exact solution for this recurrence, we're more concerned with finding the upper bound for this recurrence. And sometimes, as computer scientists, we'll concern ourselves with the lower bound or or both. But usually, O notation is enough. Okay, so O notation wise, how do we solve the MergeSort's recurrence? So we got a recurrence like so, and I guess the best thing we could do again is to unroll the recurrence. So we have something that takes n time. Then there are 2n/2 times here, and there are 4n/4 times here, and then there will be 8n/8 times here. So at every level, the total work is c to the n, right? This goes to n time. This goes to n time, or c to the n time, c to the n time. This goes to c to the n time. Okay, we're including this constant factor mainly because, merge might take 2n time, or 1n time, or 10n time. It doesn't matter. Those constants don't matter. But the thing that matters is this n. Okay, so because every level takes c to the n time, and there are, how many levels are there? Well, there are enough levels so that n goes to 1. Okay, so how many levels do we need to get n to divide n by 2 to go to 1? We need log 2, right? This is a logarithmic function. We need to progressively, if n over 2, 2k needs to be equal to 1, then we need k needs to be at least equal to log. If k is equal to log n, then n over 2 to the log n is equal to n over n, which is equal to 1. Okay, so there are log n levels. There is c to the n work at every level. And so the amount of work is c to the n times log n, otherwise known using notation as n log n. And that's what we're taught as computer engineers, that MergeSort takes n log n work. Okay? So routing back to recurrences real quick, there are a number of ways to solve recurrences. And there are basic math ways, the geometric series, which we discussed with the Tower of Hanoi part, that you could solve recurrences that way. You could expand the recurrence and spot the pattern. Again, we did that with the Hanoi, and we do that with MergeSort. But the best way, and before we get to that, there's the guess and verify. Basically, let's say we have an inkling of what the actual solution is. We could plug the solution into the recurrence and make sure it's correct, right? If we wanted to, so we could do that. Now, there are all these methods, and these are the very basic methods mathematicians use. But the biggest method that we're going to use in this course is simply the recursion tree method. Okay, which is basically expanding the recursion tree like we did, looking at the amount of work that's done on each level, then the number of levels, and multiplying those two together. And this is actually written as the master theorem in Jeff Erickson's book. Erickson's algorithms book. Okay, so that is MergeSort, and hopefully you almost definitely knew how to program MergeSort already, but hopefully now you understand how we analyze MergeSort in terms of recurrences and why the running time for MergeSort is O to the n log n. Okay? All right, see you on the next one.